Hi, and welcome to this quick review of carboxylic acid derivatives, which follows on from my clip on carboxylic acids and esters. As always, the clip's designed to be used alongside notes and independent study tasks that you've completed, and this particular one will focus on the reactions of acyl chlorides, with a little bit of extra attention paid to acid anhydrides. I also include a short section on nucleophilic addition-elimination mechanism, in which acyl chlorides react. But this is extension work only, so don't feel you have to go and learn it. It's just an interesting side note that goes with this particular set of reactions. So the acyl chloride group is basically this structure here, and it contains a very polar carbon-chlorine bond. Because of the strong electronegativity difference, or significant electronegativity difference between carbon and chlorine, the partially positive carbon atom is therefore very susceptible to attack from nucleophiles. So any species with a lone pair of electrons available for forming a dato-covalent bond will react easily with this particular carbon atom. So all of these different species have a lone pair of electrons available for forming a dato-covalent bond, and they react with the acyl chloride functional group by way of a mechanism called nucleophilic addition-elimination. So like I've said before and I've left up at the screen, this is an extension, this particular mechanism, but I'm going to use it in each case to show you examples of it in action so you can start to get a feel for what it's about. As you'd expect, it involves a nucleophile. As you'd expect, it involves addition, because you've already looked at nucleophilic addition. The elimination part of it is the interesting bit. So I'll take each of the colour-coded groups at the bottom of the screen in turn, get rid of the sort of basics about the acyl chloride functional group in the middle, and in that space I'll put in the nucleophilic addition-elimination mechanism. So let's start off with the first one, alcohols. So I've drawn the alcohol group as a nucleophile, and you can see that it's got a lone pair of electrons. So once the lone pair of electrons are attracted to the partially positive carbon, the weak or relatively weak pi bond on carbon double bond oxygen breaks, hence the second curly arrow. The oxygen atom that was on the carbonyl group, as in the C double bond O group, that's now negatively charged. At the same time, the oxygen on the alcohol, the OH, has one extra bond, so it now becomes positively charged. So that negative charge on the oxygen means an extra lone pair that wasn't there before. So the pi bond reforms between carbon and oxygen. The carbon-chlorine bond now breaks because that carbon doesn't need this bond anymore. It would have 5 otherwise, so this is a surplus bond. So the chlorine now takes both those electrons because it's more electronegative than carbon. But we have to still deal with the positively charged oxygen at the bottom. So the way this is dealt with is that the HO bond breaks with the oxygen taking both electrons. So our final products are an ester in this case, and the H plus and Cl minus that both came off the intermediate in the middle, they combine to make HCl. So the first stage is the addition, the nucleophilic addition. The second stage is the elimination. So before I actually go through all the other ones very briefly, why not pause the clip, even though it's extension, this particular mechanism, and just push yourself a little bit, see if you can work it out. I'll leave this version up there, and I'll see if you can choose from phenol, water, ammonia, or primary amine of your choosing, and see if you can write it out for your chosen nucleophile. So now, assuming that you've done that, you've paused the clip for a few minutes and had a go at something, I'll get rid of my version and I'll take you through each of the other 4. But what I won't do is a commentary for each stage of the mechanism. I'll just put the curly arrows, the dipoles, the charges, and the positive or negative charges as well, so you can just check. So I'll leave each one up for a few seconds. So this is the mechanism for your acyl chloride plus phenol. This time it makes a phenyl ester, and just like before, it makes HCl. So in the case of water as a nucleophile, this time we get carboxylic acid and HCl. So at this point, hopefully you're starting to see a bit of a pattern emerging, not only in the placement of the curly arrows, dipoles, etc. in the mechanism, but also what the products are. So in the case of an acyl chloride with ammonia, we get a product called a primary amide. Now, amines and amines will be handled separately in the course, not particularly in this clip, but it happens to be the product you get this time. So it's interesting to see that in the equation at the bottom of the screen there's 2 moles of ammonia. I haven't included them in the mechanism. The reason you need 2 moles of ammonia is because the HCl that you would get otherwise would go back and react with the ammonia. So instead of getting HCl, what we actually get is something called ammonium chloride. So if you look down at the reaction with primary amines that we're about to do in a second, there's something similar going on there, because amines are fairly similar to ammonia in that one of the hydrogens is being replaced by an R group. So essentially, you treat them in a similar way in terms of their chemistry. So again, 2 moles of your primary amine are required, and the products you get this time are an N-substituted amide and an alkyl ammonium chloride salt. So let's now sum up what you actually need to know, because I did mention, didn't I, that nucleophilic addition-elimination is actually extension. You can see I've printed it at the top of the page. So you have to know the products that you get during each reaction between an acyl chloride and a given nucleophile, and also the reason that we need 2 moles of nucleophile in the case of ammonia and primary amines, as explained in the pink and black equations at the bottom of the page. Now I mentioned in the beginning that some attention will be paid to acid anhydrides because it's worthwhile mentioning them now as well. So acid anhydrides will react in a very similar way to acyl chlorides, and they'll also do it via nucleophilic addition-elimination. So they react in a more controlled and less exothermic way than acyl chlorides, so are often preferred in some laboratory preparations for this reason. But it's important to remember too that instead of HCl as a toxic or potentially toxic byproduct, a carboxylic acid instead, based on the acid anhydride, is actually made. So this is another reason that sometimes acid anhydrides are preferred. So for example, if you react an acid anhydride with an alcohol, you get a carboxylic acid and an ester. And here's the equivalent for the reaction of an acid anhydride with phenol. So here's a little exercise to try as the clip comes to an end. If you use these equations, see if you can predict the equivalent ones for the reaction with ethanoic anhydride, with water, with ammonia, and with a primary amine. So until next time, thanks for listening. Go and have a go at those now, and see you soon.